and electric potential energy. So we have voltage and energy in this. I'll probably just do the first 5 pages and then do the next 5. So 35 is looking at the difference in electric potential. Remember, they don't even have to use the word difference. Electric potential is always the difference. So we always have to have some spot we've called, you know, of a voltage of 0. Typically infinitely far away we say is 0, and then the voltage at any spot then is the increase of voltage from that location. You know, the charges at P, the value of the electric field at positions, those have no role in the actual electric potential difference between 2 points. The potential difference comes from integrating the electric field, right? You're accumulating the electric field over a distance, which is what this is saying. And the path you take doesn't matter, meaning if you start at infinity and you go to a distance r, it doesn't matter whether you weave in and out, just like gravity with a roller coaster. It just matters what height you start at and what height you end at. Okay, this one, I know, you know, you can look at the function here. The closer you are to this positive 2Q, then you're going to have this higher voltage. Remember, voltage. The voltage here is the sum of the individual voltage. They're scalar, so we're going to have a positive voltage from this guy and a negative voltage from this guy. And as you move closer to the negative charge, well, you're just going to get an increase of voltage. There is a spot between them, like right there, where the voltage is 0. So the voltage is going to be really big and smaller and smaller and smaller, and then 0, and then really negative and negative and negative, because you get close enough to this. And really, this is what it would look like if you actually looked at the function of r, which is why it's not linear like this. It's like a 1 over r type deal. So this, you know, even if you didn't know what the curve looked like, that's the only answer that makes sense. We know it's not linear, and we know it is going to start at a high voltage, go to 0 somewhere in between, and then go all the way to a negative. Okay, so we have these scenarios, and you should be able to look at this. Remember, so the electric field is a vector where voltage is a scalar. So if you look at this guy in particular, 4 plus charges, the electric field at the center is going to be 0, but the voltage would be kq over r, where r would be the distance you are, because those are all going to add up. Where if you look at this one, the electric field is also 0, because the negatives pull, this pulls up and this pulls down, and that pushes right and that pushes left. So the electric field is still balanced, but the voltage is also balanced because there's 2 positive kq over r's and then 2 negative kq over r's. So when we look at something like this, the electric potential for these, which configuration are both electric field and potential 0 at the origin? That was this guy here. In which configuration the value of the electric field, but the electric potential is none. Okay, and that's this guy. The field is 0, but the potential is non-zero. Field and potential are 0 for that reason. Up here at the origin, the field would go to the right. Up here, the field would go this way. And up here, the field would go that way. Okay? All right, next. 2 separate. All right, so we got infinite sheets. Which graph represents the left of potential as a function of x? Okay, so here, the E field is 0 over here in this region. Remember, infinite plates have the same electric field. It doesn't matter on distance. And so all of this area over here has a voltage of 10. All of this over here has a voltage of, let's say, negative 10. Okay? Inside, as we get... the electric field is going this way, right? It's a non-zero electric field, and so we go this way. We are going to go down in voltage, and it is going to be linear because of that uniform electric field. So up here, when the electric field is 0, there's no change in voltage. Then the voltage is going to linearly drop, and then there's no change in voltage. Again, the whole idea is that these infinite sheets have electric fields that don't vary on distance, which doesn't matter where you're over here, the electric field is the same from the positive, but it's also equal in magnitude of the negative. Even though you're closer to the positive, it doesn't matter, which means the electric field is 0, which means there's no change in voltage, which means the voltage is constant over there, which means this guy makes sense. Okay, down here. An insulated conducting. Okay, so we know that inside a conductor, we have an electric field of 0. But if the electric field is 0 inside of it, that means the voltage is constant inside of it. It doesn't mean that the voltage is 0. It means that the voltage is constant. It's actually whatever the voltage was on its surface, that's what the voltage is inside. Remember, if the electric field is 0, it doesn't take any energy to move around a charge, which means the potential, the voltage, has to be the same everywhere throughout. Otherwise, charges would be flowing. And we know, there's no charge flowing. There's not even any charge inside that conductor. So this guy makes sense here. The voltage is constant when the E field is 0, and we get to the surface, and then the voltage acts like a point charge, and the voltage is like a KQ over R, right? So this is like a 1 over R or 1 over X. Okay, so this is kind of like the definition of what energy is, right? So electric potential energy, U, is equal to QV. Remember, voltage is in joules per coulomb. It tells you that if you have, let's say, a 10-volt difference and you want to take 1 coulomb of charge, you're going to have to do 10 joules of work to move 1 joule or 1 coulomb of charge through 10 volts. So in this particular case, what's the net change in kinetic energy? Well, that's just the kinetic energy comes from the loss of potential energy. Potential energy is just QV. So don't overcomplicate the world. It's just this. You tell me the charge, and you tell me the voltage that it passed through. I'll tell you how much then energy it gained, and then that would have obviously went to kinetic energy. All right. So when it says these spheres are connected by a thin wire, that means charges are allowed to flow back and forth between them. Okay, so when you have two things of different sizes, they are not going to become equal in charge. They're going to become equal in potential. Here's why. Let's say when you connect these that you still think this one is at a bigger voltage. Well, if this was at 10 volts and this was at 8 volts, you know what would happen? Charge would flow over, but it doesn't. Charge doesn't flow because they're at the same potential. They may or may not even have the same charge. In this case, since they're different sizes, they are not going to have the exact same charge on each other, but they have to have the same potential, right? That's what a wire does. It connects them electrically and allows electrons to flow back and forth, and they're going to flow until they're at the same potential. All right, this one. The work required to move a charge from R to S. Okay, so R and S are actually an equipotential line, right? It doesn't matter where you are on this line here. If you are always then the same distance you are from Q, and then the same distance you are from this one. And so all of these would be at the same voltage, whatever they would be, right? So if you're here, it's like a KQ over D plus a 2KQ over D. So all of this is at the exact same potential, which means there's no work required to move along an equipotential line. No work required to stay at the same voltage. It requires work to move a proton up a voltage, and it requires work to move an electron down voltage. At which of the following points is electric potential the greatest? Well, right here. Right, that would be the sum of those two because we know voltages. The voltage is the sum of all the individual voltage. The individual voltages are just KQ over R, and they're both positive, so you just add them up. If you go over here, then they're both kind of small because you're further away. And so that's going to be your best point, is going to be A. Concentric conducting spheres. Okay. As a function of R. Okay, so when you're inside of this guy, there's an E field of 0, and so the voltage is constant. Then you're going to fall off. In here, there's an E field that looks like a point charge, right? And that E field would come from that interior charge. And then when you get outside, well, there's no E field out here, so there's not going to be a change in voltage. Which also means that there is no voltage because there's no E field anywhere out here. So where would if you started with a voltage at infinity and you went all the way to there, well, there'd be no E field, so there would be no accumulation and you'd get a voltage of 0. Also, you could just do KQ over R, and since they're both the same amount of charge, and they're both point charges acting as if they're both from here, anywhere out here, the voltage is 0. Okay. Which of the following statements about the conductors? Okay, we already went over this. The surface of a conductor has to be an equipotential. If it wasn't, if you're telling me that you have a conductor and somehow one part was at 10 volts and one part was at 6 volts, well, then there would be the flow of charge on that conductor from the 10 to the 6, and that's just not true. Okay? The surface of a conductor has to be an equipotential surface. Otherwise, there would be the flowing of charge, and that's what this means under electrostatic conditions, meaning all the charges have already, got to equilibrium. Okay, so think about this. When we have a uniform electric field, then we know then that the voltage change can just be ED. Okay, V equals ED if the electric field is constant, right? There's no need to do an integral to accumulate a varying electric field. If it's just constant, well, then it's just the electric field times the distance is the voltage. And we know that the work done is just the charge times the voltage. Well, then in this case, the work is just QED. And just multiply those together and we get our answer. All right, we got conducting spheres are separated. Okay, so we want to look at the voltages here. This guy's got a smaller radius. Right, this has the smaller radius. So then we'll look at the voltage. If voltage is KQ over R and they have the same Q and the R is smaller, then this one has the higher voltage. So if you connected these two with a wire, what are we going to say? Well, current is going to go from Y to X. It's going to flow from a high voltage to a low voltage. Again, it's kind of like the reverse of the other questions. Again, if we have an imbalance of voltage, 10 volts and 6 volts, we know it's going to go from the 10 to the 6. And again, current is always the flow of positive charge. Right, current flows from big voltages to small voltages. Which of the following represents the magnetic electric field? Okay, so we have a sphere, and we know the charge is uniformly distributed on its surface. So then the electric field inside is nothing, and the voltage is just KQ over R. Okay. Okay, this, I don't know, that feels like these questions are pretty easy. We're looking inside the conductor, we have an electric field of 0, and we have a constant voltage, and the voltage inside is just the same as it is on the surface. And now we're outside. Well, the electric field acts like a point charge, and the voltage acts like a point charge. It's just a KQ over R, right? Just like a point charge. Those should have been pretty easy. Don't overthink those. All right, this one, voltage. We know that when we move away from this thing, so let's say we're here on this axis, we are the same distance we are from all of these little bitty DQs. So there's a little charge up there, a little charge down here, a little charge there. All the charges are spaced. And so they're all acting like point charges. So they're all KQ over R's. Voltage is a scalar, so we don't have to worry about a cosine or a sine. So it's just K, Q, and all the Q's just add up to the Q. And then the distance you are away is just that distance, this diagonal distance. And that is just how far you are away, X and A. So that's just A squared plus X squared and then square root, right? It's just the Pythagorean theorem. So this thing right here, the square root of that's just R. So it's really just KQ over R. And they're all at the same distance, which is why it makes that easy. All the little DQs are at the same distance on the circle. All right, last one, and I'm going to end this video, and then I'll do a different one for pages 6 to 10. Okay, which of the following correctly give the electric potential and electric field at the center? Okay, so when we're at the center, electric field is a vector field, right? So it cancels. They're all going to be pushed. This one pushes it down and right. This one pushes it down and left. This one pushes it up and right. And this one pushes it left and up. They all cancel because of an electric field. The voltage is a scalar. Remember, the voltage for point charges is just the sum of all the individual charges. Well, that's just a KQ over R. So you just get 4 V naught, where V naught, is the voltage due to one charge alone. Okay, I'll do a separate video for the next 5 pages.